Hey everyone, so today we are going to talk about number 4 on homework 10, which asks you to write the verification procedures for some decision problems. Before we start talking about what the actual problems are, let's talk about just what the question is asking you to do. It's asking you to write the verification procedure for a decision problem. And the verification procedure does not mean that you need to write the actual algorithm to solve the problem itself. So don't do that. That's a lot harder than what we're asking you for, which I hope you can tell because each of these problems is only worth 10 points. Instead, what we're asking you to do is we're asking you to assume that you have a solution in hand. You already have a solution to the problem. And when I say that, I don't mean a general solution to the problem. I mean a very specific solution to the very specific problem. So, for example, if you are asked to solve the traveling salesman problem, and I'm going to get into this a little more in detail here in a bit, but if you're given a very specific graph, we'll make it easy. Like this. And all of the weights, or all of the edges have some weights. We'll say 3, 2, this one is 1, this one is 2, this one is 1, and we'll say this one is 4. And you want to solve the traveling salesman problem, then your solution would be this. It would be, let's say you start here, and then you go this way, and you go here, and you go this way, and you go here, and you go this way, and you go here, and then you finish up by going this way, and you end up back where you started. And that would be 1 plus 2, 2 plus 3 plus 1. So 1 plus 2 plus 3 plus 1 got you to where you started from. And that is just 7. So if you, for example, said, all right, I have a solution to the traveling salesman problem for k equals 7. Here it is. All you want to do is be able to take this solution that you have, this alleged solution or supposed solution, and you want to put it into some sort of machine that tells you if this is actually a solution. So your machine will say basically, what is the problem itself? Well, the traveling salesman problem is, can you find a circuit through the graph with a weight of less than or equal to k? So if our k is 7, here's a circuit. You know it's a circuit because you start here and end here. And is the weight less than or equal to 7? Yes. So basically, you are going to write a machine that takes that information, this graph, this number, and the solution that we just found, which is this path, and you are going to write a machine that verifies that that is in fact a solution. So if, for example, I said same graph, same k, can I find a solution to the traveling salesman problem for k less than or equal to 7 on here? And I say, yeah, sure, here's my path. I'm going to start here, and I'm going to go here, and then I'm going to go here, and then I'm going to go here, and then I'm going to go here. You are going to write the pseudocode for a machine that says, no, that's not actually a solution where k is less than or equal to 7. So because this is 4 plus 3 plus 2 plus 1, and that equals 10. And so your pseudocode should say, no, that's not a solution. So basically, you are simply writing pseudocode for a machine that takes in a potential solution to the problem like this, And it either says true if that solution actually is a solution to the problem, or it says false if the solution is wrong in some way. That's all we're asking you to do. So you're going to assume that you already have a solution to the problem. And from there, you are going to write the pseudocode that determines if, it's not if at all, if the quote-unquote solution is correct. And I put that in quotes because that means, you know, we call it a solution, but it might not actually be a solution. Let me put this one in quotes as well. So your machine is just going to return true if the solution is correct. And I again apologize for my handwriting. Or it's going to return false if the solution is not correct. So that's all you have to do for this problem, and I hope that makes sense. And I'm going to walk you through one, and then I'm going to help you with the 4 that are actually on your homework. I'll help you with those a bit. So let's clear this screen here. All right, so the one I'm going to walk you through is called the independent set problem. And this is not on your homework, which is why I get to walk you through the whole thing. The independent set problem. And the independent set problem basically says, say you have some graph. We will use this graph again, just to give you an example. And I'll give you 2 examples to sort of show you what I mean. You want to find out what is a set of vertices. So if we have 1, 2, 3, 4, you want to find out, is there a set of vertices that equals some number k? Let's say k equals some number for right now. So there's some number of vertices where if you choose those vertices, they will not be connected to any other vertices that you have also chosen. So here our k is going to have to equal 1. And you can choose any of these vertices. So you can, you know, for example, choose number 3. And you can't choose anything else because number 3 is connected to number 1, it's connected to number 2, and it's connected to number 4. So that's the only one you can choose. You could also choose 4, and in which case you wouldn't choose 1, 2, or 3. Or if you chose 2, you wouldn't choose 1, 3, or 4. Or if you chose 1, you wouldn't choose 2, 3, or 4. So if k equals 1, then yes, there is a independent set that is one vertex where you can have one vertex and it's not connected to anything else. If k equals 2, however, we can't have that because, you know, if we chose 3, we can't choose 1 because 3 is connected to it. We can't choose 2 because 3 is connected to it. We can't choose 4 because 3 is connected to it. And same for all the other vertices. There's no combination of 2 vertices here that we could choose and they wouldn't be connected to each other. However, if we had this same graph, but we took out these 2 edges in the middle, and let me redraw my circle here a little bit. Oh, I need my pencil. If we took out these here, and we just have these 4 edges connecting these 4 vertices, then can we do k equals 2? Absolutely. If we chose 3, we could also choose 2. And since 3 is not connected to 2 or 2 connected to 3, that would be an independent set. So because these 2 are not connected to each other in any way, we can have a k equals 2. And as your graphs get more and more complicated, you can have even more. So if we had, for example, vertex 5 over here, then we can have a k equals 3 like that, and so on and so forth. So again, the independent set problem just asks you, for k equals some number, can you have a set of vertices from this graph that are not connected to each other in any way? That is, the set of vertices is equal to this number k. So that's the problem itself. Now, assume that we are given a solution to the problem. So we have given someone, here's your graph, here's your k, and they give us a solution back. All we want to do is check to see if that solution is correct. So in order to do that, let's think about what we need to know. Okay. So what do we need to know in order to determine if the solution they give us back is correct? Well, we need to be able to see the actual graph that we gave them. So if we gave them a graph G equals VE, which is how we designate the graphs with, N vertices and M edges. Or V, is the list of vertices, E is the list of edges. So that's what we gave them. So if we already know that, if we know the K that we gave them, K equals some number that we gave them, and then we have their candidate solution, which we're going to call C. In the independent set problem, what do you think the solution is going to contain? It's going to contain a list of vertices that they chose that they are claiming are not connected to each other, and that list of vertices needs to equal K. It needs to be a K number of vertices. So the candidate solution, C, is just a list of vertices. Okay, so that's going to be the input. This is all input to our machine. And our output is going to be true if the solution is correct, and false if the solution is not correct. And that's going to be the case for all of these machines that you write. So this is your output. And now we need to decide, how can we check this candidate solution C to make sure that it is a solution to the independent set problem given G and K. So one thing that we need to do before we even check about the independent set problem is we need to have a way to determine how to determine if two if two vertices are connected. Okay, so before we write the verification procedure for the independent set problem, let's just write a quick procedure that will check if two vertices are connected. And I will give you a hint about this procedure. You are going to need this in your homework 4. So even though we're not talking about any of the problems that are in homework 4, you are going to need a procedure that checks if two vertices are connected. So we're going to call this, and this I'm going to say, need for, I'm sorry, did I say homework 4? I meant homework 10. Homework 10, number 4. Okay? You need it. So write this down somewhere because I'm helping you out here. Here's your algorithm, and it's going to be called check if connected. And it's just a method. And its input is going to be, let's see, we're going to have just G equals VE, which is, a graph with V is a list of vertices, E is a list of edges. So this is a graph with N vertices and M edges. And I'll tell you, this is going to end up being O of 1. So if you use this, which you should, use this in your solutions for other problems for number 4, you can just count this as O of 1. We're going to say that we have some numbers I and j, and that's just a pair of vertices in G. So for example, if this is our G, we have vertices 1, 2, 3, and 4. Then ij will just be some pair of those vertices. So it could be 1, 2. It could be 1, 3, 1, 4, and so on and so forth. 2, 3, 2, 4, 3, 4. And it's just going to be the pair that we are checking to see if they're connected. So here's our input. Let me mark this as our input. And our output is just going to be true. Oops. True if vertices are connected, and false if vertices are not connected. This algorithm is going to be pretty easy. First of all, you can check if, and this is just pseudocode here, I is greater than n, or j is greater than n. So n right now is 4, and we've labeled them 1 through 4. So if you have some I that's 5, you're going to say, wait a minute, that doesn't make any sense. In which case you have a problem here. So if that happens, then we're going to return false, because that means that one of the vertices you picked is not even in G. But if both of the vertices that you picked are in G, then all you need to know is if G's list of edges, which is G is an adjacency matrix, so its list of edges is listed as a 2D array, and I'll give you an idea of what that looks like. Let me change to a different color here. So let's say this is G, and it's just listed like this. We have 1, 2, 3, 4, 1, 2, 3, 4, and there's just either a 0 if there is no connection between these pairs of vertices, or there's a 1 if there is. So this will be 0, this will be 1, 0, I'm sorry, 1, 0, this will be 1, 0, 0, 1, this will be 1, 0, 0, 1, and this will be 0, 1, 1, 0. So all we're doing is looking at this G, which is a 2D array, and we're saying, okay, if there's a 1, that means these pair of vertices is connected, and if not, if there's a 0, then the pair of vertices is not connected. So that's easy enough. So come back here to our algorithm. So if it's not the same color, let's see if this is the same color. If G I J equals 1, then return true. Okay, and that's it. That's really all you need. And if neither of those things are the case, you're going to return false. Now, how can you tell that this is O of 1 up here, like I said? Well, just look at the lines itself. So it only takes some constant time to check if I is greater than n, some constant time to check if j is greater than n. So this is O of 1. It only takes some constant time to check if this element of the matrix that represents G is equal to 1. So this is also O of 1. And all of these returns things also are constant time. So you can see that this is some constant time that this check if connected algorithm runs in, and so it's all O of 1. Now, again, please write this down. You are going to need this for your dominating set problem, I believe. So anyway, we needed that for the independent set problem. So let's get back to the independent set. So going back to the independent set, again, independent set, this is the verification procedure. Remember, the independent set is if you're given some graph and a number k, you just want to be able to determine, is there a list of vertices in that graph that equals the number k, such that the vertices are not connected to any other vertex in that list. So what do we need to have in order to be able to decide if a supposed solution to our independent set problem is actually a solution to the independent set problem? We need to still have G. So we need to know what the original graph was. We need to have the candidate C, the solution. And I wrote this down earlier, but I'll write it again. And remember, this is a list of vertices. And we need to have the number k that we gave. K is just some number, and we want to make sure that the list of vertices is equal to the number k. So, first thing, this is all input. Input. Here's going to be our output. Output. Just going to be true if the solution is an independent set of size k. And so I don't have to write that down again. I'm just going to say false if it isn't an independent set of size k. All right, so here's what we need to do. First of all, we need to check sure that the number of vertices is equal to k. So let's do that first. If the absolute value of C, or the size of C, is not equal to k, then we need to return false, because there's a huge problem right there, right? And think about, as you're going through these steps in this procedure, and I'll label the lines here, think about how much time they're taking. So how much time does it take to determine the size of C? Well, it's a list of vertices, and it should be k, but it could be as big as n. Remember that G has n vertices and m edges. And we always want our runtime analysis to be in terms of n. So this should be, or this could be, not that line, this line. This could be up to O of n, because we have to count each thing that's in C. And that could take us up to n things to count. So if C is not k, or if the size of C is not k, then we need to return false. If we don't return false there, then the size of C is k, which means we're good so far. We just need to check if any of the vertices in K or in C are connected. And we just wrote a separate algorithm to do that. And so this makes it pretty easy. So here's what we're going to do. We're going to have a couple loops. So for I equals 1. Again, this is pseudocode, so you don't have to actually write out the whole code. It doesn't really matter. But we're going to say for I equals 1 to k minus 1, do, and then we need a double loop because we need to check. So we're going to have basically G, I, J was the what we put into the check if connected method. And so we need to know what I is, and we also need to know what j is. So for I equals 1 to k minus 1, and then for j equals, we'll say whatever I is plus 1. So this will, say we can do I, G12, G23, G34, et cetera, and check everything. So again, if this is our graph, I'm just trying to keep this very concrete for you all, because that's the easiest way to see the solutions for these things. If this is our graph and we want to check everything, then you just say, okay, start with 1 and pair it with every single thing that it could have. 1, 2, and this is going to do that, but in a different way. So it's going to say 1, 2, and then we're going to say 2, 3, and then we're going to say 3, 4, and then we're going to start over here. So that's going to run. Sorry, let me try that again. So we're going to start at 1, and we're going to say, okay, 1, 2, 1, 3, and then 1, 4, and then I moves up, I increments. It's going to say 2, 3, 2, 4, and then I increments again. It's going to say 3, 4. So that's how you would pair up your vertices intuitively. At least I think it's intuitive to me. So hopefully it's intuitive to you as well. Anyway, for j equals I plus 1 to k, and here you can stop with I equals 3, so k minus 1, and you can stop j at 4. Because once you've checked the G of the matrix for G3, 4, you don't need to go back and you've already checked all the connections for 4. So anyway, for j equals I plus 1 to k, and so we have a double loop here, and so this first loop may take O of up to n times, and the second loop you may be also running O of n times. And so this will end up being O of n squared, but let's get to it in a moment. Okay, and then, so what do we need to do for, G12, G13, G14, et cetera, we just need to check if it's connected. So check if connected, C, I, C, J. If that equals, you don't even have to put equals, just if it's true. So if this is true, what did we say would be the case if checked if connected returned true? It would say that Ci and Cj, so these two vertices, would be connected. So if this is true, for any case, we have an issue, because there should be in the independent set, there should not be any vertices that are connected. So if this is true, we need to return false. And let me give you an example here of what I mean. So here's our graph G. So let's say that for our first supposed solution for the independent set problem, we were given k equals 2, and our C contained 1 and 2. What's going to happen is you're going to get down here, and it's going to say check if 1 and 2 are connected, and that's going to return true. So if this is true, which it is, we need to return false, because remember the independent set says that you want the number of you want the vertices to not actually be connected. So if it's 1 and 2, that's wrong. But if it's like 1 and 4, that's okay. In which case, check if connected would return false, because these 1 and 4 are not connected. So if we do that for all of the vertices in C, and they all are not connected, then we can finally return true. Okay, and just do a runtime analysis for this. So how long does it take to do check if connected? Well, we just said because we wrote out the algorithm ourselves, we know it's O of 1 time. This is O of n, and this right here, since you have to do this n times and do this n times, this is going to be O of n squared. And since this is your dominating runtime here, that's going to be your final runtime analysis. Remember, you have to give a runtime analysis for all of the problems in number 4. And so what I would recommend you do is that as you're writing the pseudocode, you ask yourself, well, how long is it going to take me to do this, if, or this for loop, or what have you? How long are these going to take me? And that will help you do your runtime analysis. So that's all we're looking for. We're just looking for you to write a machine that takes in a supposed solution and returns true if it's an actual solution to the problem, and it returns false if it's not a solution to the problem. So there's a full verification procedure for the independent set problem. Now, of course, that's not on your homework, so that doesn't help you very much, except maybe to understand what it is that we're looking for. So let's talk about what's actually on your homework. Okay. So the first thing on your homework is the dominating set problem. Dominating set problem. And I'll give you a hint here. Hint. Use check if connected method. That will help you for this problem. And I gave you that method earlier, or that algorithm earlier. And so you can just put that in your homework and say, here, I used it, and this is what I'm doing when I say check if connected. So anyway, your dominating set is where you are given a graph. So let's say that, let me think of what would be a good graph for the dominating set here. I think that might work. But let's see. So let's say you're given a graph, and I think this one would be pretty good. And some number k, and I want to differentiate this from the independent set problem. So I'm going to draw some extra things out here, etc. And some number k, and let's say our k equals, I'm just going to pick a random number. I'm going to pick one that I know will work, and I'll pick one that I know will not work. So our first one is going to be k equals 2. And dominating set problem just says, is there a set of vertices in this graph, a subset of vertices, such that if you choose those vertices, and we're only given 2 vertices that we can choose, every other vertex in the graph is either one of those vertices or it's connected to one of those vertices. So here's k equals 2. Well, let's look. And you kind of have to do this, if you're actually solving the problem. It's a little bit harder, but luckily we're not solving the problem. We're just doing the verification. But if we choose this vertex and this vertex, and we'll label 1, 2, 3, 4, 5, 6, then that would solve our problem, right? Because every single vertex needs to be either one of these vertices or it needs to be adjacent to one of these vertices. So let's check. 1 is adjacent to 4, 2 is adjacent to 3, 3 is number 3, 4 is number 4, 5 is adjacent to 4, and 6 is adjacent to number 3. And so here we have a dominating set that has the size 2 that works. So this is a good solution. Now, I don't want to delete all of those, but let's take out these x's here. Let's say, change my color. Now this is going to be kind of obvious, but if we had k equals 1, then there's no solution here, because the only solution that we can have, or the least number of vertices that we can have in our solution, as I just showed you, is 2. So if we pick this one, for example, then this is connected and this is connected. but you're still missing this one and this one and this one. Or if you picked, this one, then this is good, and this is good, and this is good, but you're still missing this one and this one. So, if you have k equals 1, then no, there is no dominating set solution here. So your job is not to write the actual machine that solves the problem, thankfully, because that is somewhat difficult. Your job is simply to write a machine that takes a supposed solution and determines if it is an actual solution to the problem. So all I'm going to do here, I'm not going to actually write out the verification steps or the runtime analysis for this problem. I'm just going to give you or talk to you about the things that you need to consider when you're trying to figure out if a supposed solution to the dominating set problem is actually a solution to the dominating set problem. So first of all, let's talk about our input. We obviously need graph G. Graph G equals VE. It has n vertices, m edges. It's generally a good idea to write this out in vertices and edges, and it's generally a good idea to write graph G as an adjacency matrix, which will be n by n. It's not an n. N. And again, remember that just looks like 1, 2, 3, 4, 1, 2, 3, 4. And it just has a 1 if these two things are connected, or a 0 if they're not. So it could be, this. So say it's something like that. That just shows you here are all the vertices 1 through 4, and here are the edges. There's one that connects 2 to 1. There's one that connects 2 to itself. There's one that connects 4 and 2, etc. Okay, so that's just what that means. Let me delete all that. Your other input that you need, obviously, is the candidate solution. And it would probably be helpful if you knew what K was, because part of the problem was finding a dominating set, a list of vertices that was equal to the number K. So you need to know what the number K is in order to check it. And C probably here is just going to be a list of vertices, right? Because all you have to do to solve the dominating set problem is pick some vertices. And your output, again, is going to be true if C is a dominating set of size K, and false if it isn't a dominating set of size K. Now, I've given you this. Think about what do you need from there to make a verification procedure for the dominating set problem. What should you, when you look at a potential solution to the dominating set problem, what do you need to look for? You need to make sure that obviously C, the size of C equals K, and you need to make sure that for every pair of vertices in G, so for every pair of vertices in G, I won't say every pair. We need to look at every vertex itself. So for every vertex in G, remember you have a list of vertices, it's right here. Okay, it's B. So for all, this is a little v and big V, so that's a vertex, and these are your vertices. For every vertex in G is that vertex either one of the vertices in C or connected to a vertex in C. If both of these things are true, if the size of C equals K, and if every vertex in G is either one of the vertices in C or is connected to a vertex in C, then you have a dominating set, I would argue. So your job, I'll give you all of this information, and your job is simply to take this information and put it into pseudocode. So I'll leave that to you. Let's talk about the traveling salesman problem. Okay. Traveling salesman. And this is usually abbreviated TSP for traveling salesman problem. And here's what the traveling salesman problem says. You are given some graph, and it has to be a completely connected graph, or so that's what this looks like. It means that every single vertex is connected to every other vertex, like that. And each vertex is, or each edge is given some weight. And we talked about this earlier in the video, but I will just put it up here again. This is 1, and this is 2. And your job is to, so to solve the traveling salesman problem, what you have to do is find a cycle in the graph, and a cycle is where you start at one vertex and you end up at the same vertex. And you want to only visit each other vertex once. That visits each vertex once. And you are given some number k. Okay, so let's say over here k equals some number. Okay, find a cycle that visits each vertex 1 and has a total weight of less than or equal to k. All right, so that's your job. So here, let's say you're given k equals 4, for example, and you just want to find, you want to see if there is a cycle that gives you, it visits each vertex once and has a total weight of less than or equal to 4. So let's say that we start here, and we're going to go here, and we're going to go here, and then we're going to go here, and then we're going to go here. So let's just say we do that. That's going to give us 1 plus 2. It would help if I labeled these more clearly. This one right here is 2. Plus, and we go up here, so that's 1. And we go down here, so that's 1. So if you were given this potential solution to the problem, the TSP problem with k equals 4, this obviously equals 5, and so it would end up not being a good solution. However, I don't believe there is a solution. Let me see. There's not a solution that visits every vertex 1 and gives you a total weight of less than 4. However, if you're given like k equals 6, for example, so that's bad, wrong. If you're given k equals 6, then you can find a cycle for which every vertex is visited once and your total weight is less than 6. So since 5 is less than k here, that's fine. So your machine wants to check, this solution to make sure that A, there is a cycle, which means you start and end at the same place. B, each vertex is visited once. And C, your total weight is less than or equal to some number k. So with that being said, and again, I've kind of given you all the information that you need here, and you just have to put it all together. But with that being said, I'm going to give you the input and output, and I'll leave it to you from there. Input is, again, going to be your original graph. And that's going to have, in vertices, and it's also going to have, it's not going to be in, it's going to be, so this will be in vertices, and it's going to be n times n minus 1 over 2 edges. You can call that m if you want to, but that's what it's going to be. And it may help you to know that m is in the big O of n squared. I talked with you a little bit about that on the last video. So if you are not sure, if you don't believe me about this, go to the last video or just try it for yourself. See, how many vertices or how many edges you need to fully connect a graph with some number of vertices. But anyway, you're going to have this list of vertices, this list of edges. G you can represent as an adjacency matrix. You're going to have n vertices and m edges, and your m is going to be this number. And you are also going to have, of course, your candidate solution. Which we can call C, and we're going to draw this way out here. And you need to know your number K. So ugly looking K. K is going to be some number, some non-negative integer. And your output, again, is just going to be true if C is a cycle that visits each vertex and has total weight of less than or equal to K, and again, false if not. And so just all I want you to do is just think about what do you need to know to figure out if this candidate solution C has these things. Well, first thing, is it a cycle? Is it a cycle? And there's an easy way to check for that, but I'll leave it to you to sort of figure out how to do that. Does it visit every, sorry, my handwriting is terrible tonight. I think I'm just tired. Does it visit every vertex? And is the total weight less than or equal to K? So, here's what you need to determine to see if C is a actual solution. And I'll leave you to write the pseudocode for that. The next one is, let's see. Your next one is your 3-color problem. So let's talk about the 3-color problem. And again, we have talked about this in the previous video, kind of a little bit. I'll talk to you about it again. So let's say, write this up here, 3-color problem. All right. Let's say that you're given some graph G, and it has some vertices and some edges, and we'll actually draw out a specific G here. So here's a G. Okay, we'll just make it like that for right now. And we want to know, the 3-color problem asks, can we color each vertex such that no 2 vertices, I'm sorry, let me make that more specific, no 2 connected vertices are colored the same color and we only use up to 3 colors. That's the 3-color problem. So let's just talk about what that would look like, what a solution to this would look like. So let's say we have our 3 colors. Let's say since our graph is pink, our colors are going to be blue and green and orange. Can we color this graph G so that no 2 connected vertices are colored the same color and we only use up to 3 colors? Well, let's try it. So let's say we make this one orange. And we can't color this one orange or this one orange or this one orange because they're all connected to this first one. So let's pick a different color. So again, we're allowed up to 3 and we said they're going to be orange, green, and blue. So let's say we make this one blue. Okay. I hope that looks blue to you. It might look kind of purple. So now we have these 2 colors, orange and blue. And we've already decided we can't make this one orange or this one orange or this one orange. And now we know we can't make this one blue or this one blue or this one blue. That's fine here because that's an orange, and so it's not blue. But we can't make this one here a blue, and we can't make this one here a blue. Oops. So what can we do? Well, let's switch to our third color, green. Okay, if we use green, let's color green here. Okay, now we know that this one can't be green, which is fine because it's orange. And this one can't be green, which is fine because it's blue. But this one's not connected to this one, and so this one can also be green. And so we have seen that given this graph G, we can color each vertex such that no 2 connected vertices are the same color, and we only use up to 3 colors. Okay, so we found a solution for this problem, and what you would want to do is say, okay, I have this supposed solution to the problem, and I want to check to make sure that it is a solution. Now, say for example that our graph was slightly different. Let's say that instead of this graph, it was this graph. Now what could we do? Well, so we've colored in this one orange and this one blue. This still can't be orange or blue because it's connected to both. This one can't be orange or blue because it's connected to both. So we can pick our third color, green. Color in that one green. But this one cannot be green because it's connected to the green one. It can't be orange because it's connected to orange. It can't be blue because it's connected to blue. So here we cannot solve the 3-color problem. But anyway, that's not what we're checking for anyway. We are just, saying we have a potential solution, and we just want to check to see if the solution actually works. So that's the 3-color problem itself. Let's talk about the solution to the 3-color problem, or the verification step to this 3-color problem. So again, I'll give you your input and output, and I'll give you some hints, and I'll leave it to you to sort of figure it out from there. So let's talk about our input. Input. Again, you're going to have your original graph G equals VE. You're going to have, N vertices, M edges. It can be an adjacency matrix of, size N by N. You can list all that out if you want to, or you can just keep it in mind. It's up to you. You're also going to have your candidate solution C. And let's think about what we need C to be. So for the last couple of problems, it was, or at least for the dominating set problem, it was just a list of vertices. For the traveling salesman problem, it needs to be a little different because it needs to be a list of edges and the edges weights that you take. And so it could be, a list of paired vertices, which represents an edge, and the edge itself. Sorry, I didn't write that up there for you. Anyway, in the 3-color problem, you need to have a list of colors of the vertices. So you have some candidate solution C, and we can say where C sub I refers to the color of vertex I. So, to give you an example here, we switch colors and draw G again. If this was your G, and you have 1, 2, 3, 4, and you had them all different colors. So let's say number 1 was green, and number 2 was blue, and number 3 is also blue, and number 4 is orange. Then your candidate solution would just kind of look like this. It would say, I'm going to write it over here, C1 equals green, C2 equals blue, C3 equals blue, blue, C4 equals orange. Okay, so that would be sort of your candidate solution there. And then you would also need to, really don't need this because this would be a constant, but when you're given the k colorable problem instead of the 3 colorable problem, you have some number k that's not a constant, but here k is always going to equal 3. So you can leave that in if you want to, or you can take it out. It doesn't really matter since it's a constant. And your output, and this is going to be, true if C is a coloring of the graph such that, what do we need to know? All vertices are colored, no two connected vertices have the same color, and there are less than or equal to 3 colors. Okay, and then again, false if not. So what do you need to check here? Well, it's all up here in your true statement. You need to check are all vertices colored? You need to say are any 2 connected vertices the same color, and are there only instead of saying only, let me say, are there less than or equal to 3 colors? So if you can answer those 3 questions, then you know the answer to your, if your candidate solution is a correct solution or not. So your job, again, is to write these 3 questions into pseudocode and do the runtime analysis. And that is the 3rd problem. That's part C of number 4. And so finally, let's look at part D of number 4. So part D is the set cover problem. And the set cover problem basically gives you some set. So let's write this out here. Set cover problem. And you are given some set, so we'll call it S. And we'll just say S equals, and there's the homework actually gives an example here. And so I'm just going to use the example. Let me go find it. We'll say S equals 1, 2, 3, 4. That's our set. And you have some family of subsets, F, And that we can say for right now, and we'll change this to sort of show you how this works. We can say is 1, 2, 2, 3, just number 4, and the last one we have is 2, 4. Okay, and the question is there some set k, so we have k equals some number, again, some non-negative integer, some set that is k elements large or less, that is subsets from F, that if you put them together, if you union them, you will get S. So let's say, for example, k equals, let's see, what's the smallest number here? We're going to need 3 equals 3. If we have k equals 3, let me put that all in a different color so I can show you what I'm talking about. If we have k equals 3, then the answer is going to be yes. There is some subset from F that is less than or equal to 3 elements, that if you union them all together, you will get S. And here it is. 1, 2, 3. Okay? Union these all together, you will get S. So how do you do that? You look at, unioning these. So you'll get 1, you'll get 2, you already have 2, you'll get 3, and you'll get 4. You could also do these, and that will give you the same thing, 1, 2, 3, and 4, which is all the elements of S. But if your k, for example, is 2, the answer is going to be no. There's no 2 elements in F that will give you S if you union it all together. You can't do these 2 because that's just going to give you 1, 2, and 3. You can't do this one and this one because that's going to give you 1, 2, 4. This one and this one will also give you 1, 2, 4. These 2 will give you 2, 3, 4. These 2 here will give you 2, 3, 4. And these 2 here will give you just 2 and 4. So there's no pair of elements from F that when you union them, you get S. If, for example, that was instead this, 3, 4, then there would be a subset of F that can be unioned to give you S. It would be this one and this one. That gives you 1, 2, 3, 4. However, since that wasn't originally in there, the answer for that is no. So again, that's not the problem that you want to solve. Your problem is taking some solution to some potential solution to the set cover problem and checking to see if it's an actual solution. So let's talk about how we can do that. So for our set cover problem, you are going to need, so you're going to need your original set. Let's see, this is input. You're going to need your original set, S, and that's a set of integers of size n. You're going to want your candidate solution. Candidate solution. And basically, this is just going to be a list of subsets from your subsets F. So this is just going to be a list of subsets from F. You want to know what your K is. And again, that's some non-negative integer. And you can put in F if you want to. So if you said, you also want F, which is your list of subsets from S, so that, you know, we had S was 1, 2, 3, 4, and then we had F is, you know, 1, 2, and 2, 3, and 4, and 2, 4, etc. You can use that as well. So anyway, you have input, and you have your output, and it's just true if C is a list of subsets from F that when unioned gives S, and we'll say, you know, we need this list to be less than or equal to K. So, and the size of C is equal to less than or equal to K. Okay, and then it needs to be false if not. And so what do you need to check here? You need to check to make sure that your size of C is less than or equal to K. You need to check and make sure that you can check and make sure that your subsets in C are also in K, not K, sorry, F. And you want to check and make sure that union of subsets in C give you S. And remember that we're not talking about graphs anymore. We're just talking about a list of integers. And so that should make it a little bit easier to think about how to check for these things. You know, so when you're checking, for example, the union of subsets in C should give you S. You just need to make sure that for every integer in S, it is somewhere as well in C, right? So after you've checked all this, and you can check, is every integer in S also in C? And that will be a pretty easy way to see about number 3 here. So again, your task is to write this up in pseudocode and do a runtime analysis. So again, that's all of question 4. If you have any questions after watching this video, please come to office hours and let me know, and I will help you work through them. Otherwise, I hope that you do well. Thank you.